Hello, I'm Arun, and I will make a presentation about nanocantilevers and nanosensors. I am studying at Ege University, and my department is mechanical engineering. These are my contents, and my main topics are nanocantilever sensors, how does a cantilever work, and can a nanosensors warn us about tsunamis? What is nano? If we want to understand that what is nanotechnology, we need to know scale of this. We call it nano. Nano is an SI prefix and comes from the Greek word for dwarf. 1 nanometer is 10 over minus 9 meters, or about 3 atoms long. Here are comparisons will help us to understand how small a nanometer is. An average human hair is about 60,000 and 100,000 nanometers wide. Our fingernail grows a nanometer every second. A sheet of paper is about 100,000 nanometers thick. In 1 inch, there are 25,400,000 nanometers. What is nano? If we want to understand that what is nanotechnology, we need to know scale of this. We call it nano. Nano is an SI prefix and comes from the Greek word for dwarf. 1 nanometer is 10 over minus 9 meters, or about 3 atoms long. Here are comparisons will help us to understand how small a nanometer is. An average human hair is about 60,000 and 100,000 nanometers wide. Our fingernail grows a nanometer every second. A sheet of paper is about 100,000 nanometers thick. In 1 inch, there are 25,400,000 nanometers. Nanotechnology and nanoscience. Nanotechnology has the potential to completely change the world around us. Already, nanoscale technologies have revolutionized medicine by allowing for the detection of bacteria in bloodstreams and potentially even cancer. They have changed drug delivery, and nanoparticles are even used in sunscreen. Futurists and sci-fi fans even dream of a futuristic age of nanorobots that can manipulate matter on the molecular level, potentially giving rise to nanofabrication of a vast array of different products. Nanotechnology is often divided into two parts. Nanoscience, where researchers learn about the chemical, physical properties of materials at the nanoscale. Material at 1 and 100 nanometer are called nanostructures. They are smallest things that can be made. Nanotechnology, where researchers develop and apply materials at this scale to develop new products or methods. How is nanotechnology started? Many people trace the origin of the field of nanotechnology to a famous lecture given by visionary physicist Richard Feynman back in 1959, entitled "There is Plenty of Room at the Bottom." In the talk, Feynman speculated on the possibilities of manipulating matter on the molecular scale, approaching the physical limits of what could be achieved. Feynman discusses miniaturizing computers. He predicts that manipulating materials on the atomic scale will give rise to a whole range of properties. Richard Feynman said this about nanotechnology field. What could we do with layered structures with just the right layers? What would the properties of materials be if we could really arrange the atoms the way we want them? They would be very interesting to investigate theoretically. I can't see exactly what would happen, but I can hardly doubt that when we have some control of the arrangement of things on a small scale, we will get an enormously greater range of possible properties that substances can have, and of different things that we can do. Nevertheless, the ethics of nanotechnology remains an important consideration as it becomes ever more pervasive throughout manufacturing and engineering. As with most fields of technological endeavor, the great benefits that nano-engineered structures can provide also come with a responsibility to use the technology wisely. The journey of nanotechnology began as a dream in the 1950s. Parts of that dream have already been realized. It remains to be seen definitely how much is possible and practical through manipulations on the atomic level. Let's start with one of the main topics, nanocantilever sensors. Researchers have made a discovery about the behavior of tiny structures called nanocantilevers that could be crucial in designing a new class of ultra-small sensors for detecting viruses, bacteria, and other pathogens. The cantilever, which looking like tiny diving boards made of silicon, could be used in future detectors because they vibrate at different frequencies when bacteria, viruses, and other kinds of stuffs stick to them, revealing the presence of dangerous substances. Because of the nanocantilever's tiny size, it is more sensitive than larger devices, and this sensor is enough to detect a single virus molecule, promising the development of advanced sensors that detect minute quantities of a contaminant to provide an early warning that a dangerous pathogen is present. Cantilevers are fabricated from various materials. The most common materials used are silicon and polymers. If we have hundreds of these nanocantilevers and coated each of them with a compound that different types of molecules like to stick to them, we could detect these different diseases in human breath all at once. The basis of the most chemical and biological sensors is that the transducers is coated with a chemically sensitive layer that will react with target molecules. The researchers were surprised to learn that the cantilevers coated with antibodies to detect certain viruses attract different densities or quantity of antibodies per area depending on the size of the cantilever. The devices are immersed into a liquid containing the antibodies to allow the proteins to stick to cantilever surface. There are two main criteria required for a successful sensor: sensitivity and selectivity. Sensitivity characterizes the response of the sensor to target molecule. Highly sensitive sensors provide a large signal to small concentration of target molecules. A sensor's sensitivity increases as its surface area to volume ratio increases. How does a cantilever work? It's a hanging cantilever connected to a substrate, and when a biomolecule lands on the sensor surface, just like diving board, when somebody stands on the end, the cantilever bends. So you can see this diving board in the picture. Here it's a virus. If biomolecule lands on the sensor surface, it will change the deflection and resonant frequency. This added mass is deflected in the frequency of this cantilever, and that allows us to detect its mass. Remember, this is a very small mass, and still sensor is sensitive enough to detect a single virus molecule. So how do we measure the deflection? Once the biomolecules have landed, it will deflect the beam, and after that light will start to bouncing. This light will land somewhere on the screen of the photodetector. After it has bent, we are able to measure the location, and from there we can calculate what the resonance frequency is, or how much deflection has. This is one of the ways to find deflection. Cantilever sensors has typically two operating modes. One is the vibration mode, which measures the resonant frequency changes. The second operation mode of the cantilever beam is bending mode, which measures the static deflection of the beam. This mode very useful, especially in biotechnology applications. A cantilever beam is one of the simplest mechanical structures. If a force F is applied at the free end perpendicularly to the beam, Z will be the deflection of the cantilever. E is the Young's modulus for the beam. When a biomolecule arrives on end of a cantilever will oscillate at a frequency determined by cantilever characteristics and mass of the biomolecule. As more and more target material attached to the surface, cantilever gains mass. As the mass increases, the resonant frequency of the cantilever decreases. So let's start my last main topic. Can nanosensors warn us about tsunamis? Firstly, we need to discuss about what will cause to happen to tsunamis. Tsunamis are giant waves caused by the displacement of a large volume of water, generally in an ocean. Earthquakes, volcanic eruptions, and other underwater explosions have the potential to generate a tsunami. So, how can we understand when it will come? Recent development in deep ocean measurement technology with tsunami forecast models have demonstrated that tsunami impact can be predicted before the tsunami reaches the coastlines. Tsunami forecast models are based on observations that are typically 1,000 km or more from the earthquake epicenter. Nano-resolution pressure sensors have the necessary resolution to distinguish between tsunami, seismic signals, and ocean noise in the near field. This study describes the result of a 17-month experiment that was initiated at the Monterey Accelerated Research System. The experiment compared a conventional pressure sensors at a depth of approximately 900 meters. The results presented include examples of near and far-field earthquakes and micro-tsunamis that were detected by the nano-resolution pressure sensor. They will also improve the identification and prediction of the magnitude and location of natural disasters such as earthquakes and tsunamis with increased warning times. While power requirements of the nano-resolution sensors are higher, it is also capable of recording data at much higher sampling rates. This resolution allows scientists to better distinguish between oceanographic signal or noise and seismic events for improved tsunami detection and modeling. The nano-resolution pressure sensors are able to measure ocean signals with fine scale of clarity, including the detection microseism, it means earthquakes that magnitude low, infragravity waves, and earthquakes. The nano-resolution pressure sensor is able to distinguish pressure changes equivalent to a fraction of a millimeter that are the result of microseism and infragravity waves. As you can see, if we look at the diagram, we can understand that nano-resolution pressure sensor is more sensitive than the standard one. The Monterey Accelerated Research System consists of a 52-kilometer undersea cable that carries data and power to Monterey Bay. More than 8 different science experiments can be attached to this main hub. These experiments have shown that seafloor measurements of absolute water levels, tides, infragravity waves, microseism, and signals from distant and nearby earthquakes can be made with greater accuracy than previous one. Earthquakes can produce dynamic pressure variations which are infrasonic acoustic waves. These waves, produced by local earthquakes with magnitudes as low as 3.0, have been detected by the nano-resolution pressure sensors at Mars. At longer periods, the entire water column above sensor moves up and down in response to the passing tsunami wave train with an amplitude that can be computed from the seafloor. Accurate time series of a tsunami signal for a comparison with a pre-computed model scenarios are the basis of the forecast system. The high-frequency earthquake signal is noise for tsunami detection process. With standard sensors, this noise overwhelms the tsunami signal, making tsunami detection difficult. The improved temporal sampling and vertical accuracy provided by nano-resolution pressure sensors shows promise for tracking the earthquake vibrations while recording the tsunami signal, opening the possibility of earlier. These are my conclusions. The experiments shows that nano-resolution's pressure sensor is a good vertical ocean bottom seismometer. The depth sensor provides measurements of tsunamis, and nano-resolution pressure sensors provide sufficient data for early detection, evaluation, and forecasting earthquake-triggered tsunamis. Cantilever sensors measures change the mass at the beam, and we can define that which molecules or pathogens we are dealing with. I think nanocantilevers could be the most important invention at nanotechnology field, because these cantilevers help us to identify viruses, bacteria, or other pathogens. So I believe that one day we will defeat the cancer, and cantilever support will be huge. These are my references. Thanks for listening, and keep believing in science and technology.